You know that phone in your hand, or the computer you're watching this on? Have you ever really truly stopped to think about what's going on inside? Today, we're going to look inside. I mean, really look inside. We're going to zoom past the glass, past the circuits, all the way down to a scale so small that the normal laws of physics just break. We're going on a hunt for the invisible quantum engine that powers our entire digital world. So let me just ask you, straight up, what's really making that screen light up? What is processing all the information that lets you see and hear me right now? And the obvious answer is electricity, right? A battery, a plug in the wall. And yeah, you're not wrong, but that's barely half the story. The real answer is much, much stranger. That's right. The device in your hand, on your desk, isn't just a clever piece of classical engineering. It is a full-blown quantum machine operating in a world ruled by the bizarre laws of quantum mechanics. Okay, so to see how this works, we need to zoom in, and I mean way, way in. We're leaving the world we can see and touch and heading down to the nanometer scale to find this invisible engine that makes it all tick. So inside the main chip of your device, there are billions, that's with a B, of tiny little electronic switches called transistors. To put that into perspective, you could fit millions of them on the period at the end of a sentence. It's wild. They are the fundamental building blocks, the microscopic brain cells of our entire digital world. And here is the absolute key. When you get this small, the predictable, comfortable rules of physics that run our everyday lives, a ball rolls downhill, that kind of thing, they just stop working. The quantum world is a much stranger, much more unpredictable place. For decades, the guiding light for the entire tech industry was something called Moore's Law, which basically said, just make transistors smaller and smaller. But eventually, engineers slammed headfirst into a fundamental wall, a physics wall. This quote really gets to the heart of it. I mean, think about it. You can't design a reliable switch if you have no idea how the very thing you're trying to switch, an electron, is going to act. And at this tiny scale, classical physics was suddenly giving engineers all the wrong answers. See, at the quantum level, an electron isn't just a tiny speck of dust. It's also a wave of probability. So it stops behaving like a predictable little billiard ball and starts acting more like a ripple in a pond. It has a chance of being in many places all at once. So how do you build a precise switch out of that? Well, the answer was, you don't fight it. You embrace it. Engineers had to literally throw out the old classical rulebook and pick up a new one. The rulebook of quantum mechanics. This wasn't just abstract theory anymore. It became their practical, day-to-day engineering manual. One of the first new rules they had to master was this idea of energy bands. The easiest way to picture it is like a building. In a material like silicon, electrons are only allowed to live on certain floors. Those are the energy bands. But they can't just hang out in between the floors. That space is a forbidden bandgap. And this chart here shows why silicon is the magic ingredient. In a conductor, like a metal, there's no band gap. Electrons flow freely. It's always on. In an insulator, like glass, that gap is huge. Electrons can't make the jump. It's always off. But silicon, it's got a small and, this is the key, controllable gap. We can give electrons just enough of a push to hop across, turning the flow on or off. And that is our switch. And how do we control that gap? With a cool process called doping. This is where we intentionally sprinkle in just a few atoms of another element. Think of it like adding a tiny little step stool that makes it way easier for the electrons to make that jump. This allows us to tune the conductivity with incredible precision. But this is where the story gets even cooler. Sometimes the weirdest rules of quantum mechanics create the biggest problems and also the most brilliant solutions. We're about to see how a major, frustrating bug became one of the most important features in modern tech. Remember how electrons act like waves? Well, because of that wave-like nature, they can do something that seems impossible. They can tunnel right through a solid barrier they shouldn't be able to cross. For a transistor, this is a total disaster. It's like having a leaky faucet, constantly dripping electrons, wasting power, and creating heat. But then some absolute geniuses asked, what if we could control that leak? What if we used this weird tunneling effect on purpose? And that is exactly how the flash memory in your phone was born. We apply a voltage to intentionally push electrons through a barrier, trapping them on this tiny little island called a floating gate. If electrons are trapped there, the memory cell reads as a 1. If there are no electrons, it's a 0. So get this, that quantum bug, the thing that was driving engineers crazy, is the very reason all your data, your photos, your apps, it's all still there when you turn the power off. The electrons are trapped in those tiny quantum prisons until you give the command to let them go. But the story doesn't end there, not by a long shot. As we push transistors down to the size of just a few atoms, we are constantly running into new quantum challenges and discovering incredible new quantum opportunities. This is the real frontier. Today's chip designers are wrestling with a whole new level of quantum weirdness. I'm talking about things like quantum noise, where particles can literally just pop in and out of existence, or trying to manage heat when your components are only a few atoms wide. Plus, when you're building with individual atoms, no two transistors are ever perfectly identical. And the solutions are just as clever as the problems are hard. We've already moved from flat 2D transistors to these 3D structures called FinFETs, which act like fins to give us more control over that electron flow. Next up, we've got gate-all-around transistors that completely wrap the channel. Think of it like gripping a rope with your whole hand instead of just your fingers. And in the future, we might not even use the electron's charge anymore, but another quantum property called spin to do our computing. Which leaves us with one final big thought. For 60 years, we've basically treated quantum mechanics as this big problem to be engineered around. But as we've seen, it's also the source of our absolute greatest innovations. So the real question is, as we hit the absolute physical limits of what we can do as silicon, are we at the end of the road? Or are we really just getting started on a whole new one?